We are the most complex creature on this planet. A big-brained, two-legged mammal. We've risen from the raw materials of the earth to dominate and shape it. Wind the clock backwards, and the story of how we got to be us is a puzzle that defies all logic. Through nearly 4 billion years of evolutionary twists and turns, disasters strike. Predators threaten to wipe us out. From rodent to reptile, we face extinction at every turn. From the land into the water, fighting to survive every step of the way. From fish to worm, back to the very first spark of life. To a single, simple cell. This is the most extraordinary and probable story ever told. The story of mankind rising. "4 billion years ago, a ball of rock and dust spins in the frozen vacuum of space. This isn't Mars or Venus. This hell is Earth. This seething, lifeless mass of molten lava will become home to nearly 9 million living species. But generating life from this will take a chain of events that defies the laws of probability. There are many theories. Nobody knows exactly how or where life began. But it couldn't happen without water. Experts believe asteroids or comets delivered it here. The water is churning with chemicals and organic compounds. Lightning strikes the chemical soup at the right place and the right time. Billions of volts of electricity trigger a chain of improbable coincidences. The chemicals' atoms join up in a precise sequence, creating a bundle of genetic material. These fragile genes don't stand a chance in this extreme environment. But luck strikes again. A blob of oily material engulfs a single chain to create the first ever cell. Now, the genes send out messages, chemical instructions. And 3.5 billion years ago, they do something extraordinary. They copy themselves and the cell to create a perfect clone. This is the very first living thing. Every human, every animal, every bug, every plant can trace its origins to this single cell. The genes tell each cell to reproduce, guaranteeing their survival as they pass from one generation to the next. For 2 billion years, the only living things are simple single cells. But a random accident changes everything. 2 cells merge. Their genes combine. The merged cell clones itself. Its offspring contains genes from not 1, but 2 cells. 2 parents. We call this accident sex. Sex introduces variation. Occasionally, things go wrong. As the cells reproduce, genes get deleted, duplicated, These cells are mutants. Mutations pile up, differences increase, until the cells become so different, they're separate species. The tree of life branches out into billions of species, but only one will lead to us. Mutating and diversifying, spreading out through the oceans, getting bigger, more complex, until our ancestor is a 3-inch long water worm. This is us 550 million years ago. Mutations create distinct male and female sexes. We produce more offspring, passing on more genes. Mars and Venus, boy meets girl. It all starts here. But finding a partner is almost impossible when every living thing is blind. In this sea of darkness, the ability to see will give us a critical advantage. Nature's most perfect innovation begins to take shape. A handful of skin cells mutate. Now, we can tell dark from light, find more prey, dodge more predators. We live longer and produce more offspring. Soon, creatures with light-sensitive cells dominate the population. Over countless generations, more mutations refine the cells. This is natural selection in action, the process that allows every living thing to adapt to the world. And that gives our ancestor eyes. We can see, and everything we can see is descended from that first single cell. But we need to make sense of what we're seeing. Behind our eyes, a tiny collection of nerve cells cluster together. They're no bigger than a pinhead. One day, this will be nature's most complex and mysterious organ. 521 million years ago, this is the very first brain. We are a fish-like creature called mitochondria. Our brain can make simple decisions, process basic information. But we can't outwit or outrun this. Anomalocaris, the great white of the ancient oceans. Our odds of extinction are far higher than survival. Of all the species that have ever lived, 99% of them are extinct. But a lucky roll of the genetic dice helps Milo toughen up. Your jaws, your teeth, they exist because over 400 million years ago, we faced the wrath of a primeval monster. Jaws and teeth mean more food and a bigger, stronger body. Until 375 million years ago, we're a foot-long armored fish. We look invincible, but we're not. Now, the choice is simple. Get out of his way, or die. We're safe in the shallow water. Or are we? The water's stagnant. There's not enough oxygen. Starved of oxygen, cells shut down. Toxic carbon dioxide saturates the blood. We can't go back. We can't stay here. There's only one place left for us to go. It takes over 3 billion years for our ancestor to evolve from a single cell to a foot-long armored fish. Now, our future looks bleak. But natural selection throws us a lifeline. Over millions of years, thousands of generations, our body adapts until we do something no fish has done before: breathe air. The air travels into a new organ, a lung. Take a breath, and remember it's because a monster fish chased our ancestor into the stagnant water, forcing them to breathe air. We're an ichthyostega. We can breathe air or water, closing off our windpipe to switch between lungs and gills. Today, our gills are gone, but the mechanism remains, and sometimes it spasms, giving us the hiccups. 365 million years ago, we stick our head out of the water. There's a swamp behind us, paradise ahead. The choice is simple, but the consequences are immense. We pull ourselves out of the water and change the course of history. This is the moment we leave the water for a new life on land. But all this food comes at a price. The fierce sun dries out our skin. The hard terrain tears at our soft feet. Ichthyostega is a fish out of water. We dodged extinction in a stagnant swamp, only to slam straight into another deadly environment.
Millions of years before industry, agriculture, and civilization, the world stage was set for one creature's unprecedented rise. The story of humanity's evolution began about 7 million years ago, when the human lineage broke away from that of chimpanzees. Over time, an ensemble cast of over 20 early human species, or hominins, came to the fore. Most became extinct, while others might have been ancestors to today's humans. Each species exhibited varying degrees of human-like physical and behavioral traits, such as large brains, small teeth, bipedality, and tool use. These hominins fell into 3 major groups: early hominins, Australopithecines, and Homo genus. Humanity's earliest relatives lived between 7 and 4.4 million years ago in Africa. Having most recently shared a common ancestor with chimpanzees, they had many ape-like traits, such as a small cranial capacity, However, fossils show that some ancient hominins were also beginning to show human-like characteristics, such as small canines that were likely used more for eating and not for hunting or fighting. The next phase of hominin evolution involved primates called Australopithecines. They lived between 4.4 and 1.4 million years ago across the African continent. Like their ancient brethren, Australopithecines had some ape-like traits. However, changes in the skull, spine, and legs indicate a notable shift toward a very human-like trait, consistent bipedal locomotion. The third and current phase of human evolution involves members of the genus Homo. The earliest Homo species likely date to more than 2 million years ago, making them a contemporary of some Australopithecines. But unlike earlier hominins, who exhibited a mosaic of ape and human-like traits, Homo species were becoming distinctly more human. Their cranial capacity was growing larger than any other hominins. They developed sophisticated stone tool technology, and they became the first to control fire. These physical and behavioral adaptations, along with advancements in technology, allowed some Homo species to be the first to migrate out of Africa and explore the rest of the world. While a cast of over 20 hominin species have walked this earth, only one remains. Homo sapiens, shaped by millions of years of evolution, embarked on a journey of exploration and industry its ancestors could have only dreamed.
Lightning strikes the chemical soup at the right place and the right time. Billions of volts of electricity trigger a chain of improbable coincidences. The chemical's atoms join up in a precise sequence, creating a bundle of genetic material. These fragile genes don't stand a chance in this extreme environment. But luck strikes again. A blob of oily material engulfs a single chain to create the first ever cell. Now, the genes send out messages, chemical instructions. And 3.5 billion years ago, they do something extraordinary. They copy themselves and the cell to create a perfect clone. This is the very first living thing. Every human, every animal, every bug, every plant can trace its origins to this single cell. The genes tell each cell to reproduce, guaranteeing their survival as they pass from one generation to the next. For 2 billion years, the only living things are simple single cells. But a random accident changes everything. 2 cells merge. Their genes combine. The merged cell clones itself. Its offspring contains genes from not 1, but 2 cells, 2 parents. We call this accident sex. Sex introduces variation. Occasionally, things go wrong. As the cells reproduce, genes get deleted, duplicated. These cells are mutants. Mutations pile up, differences increase, until the cells become so different, they're separate species. The tree of life branches out into billions of species, but only one will lead to us. mutating and diversifying, spreading out through the oceans, getting bigger, more complex, until our ancestor is a 3-inch long water worm. This is us 550 million years ago. Mutations create distinct male and female sexes. We produce more offspring, passing on more genes. Mars and Venus. Boy meets girl. It all starts here. But finding a partner is almost impossible when every living thing is blind.
During ejaculation, nearly 300 million sperms move from the testes through the tubes called the vas deferens into the area of the prostate. At this point, the prostate contracts, closing off the opening between the bladder and the urethra, releasing fluid into the urethra and pushing semen on through. The seminal forms a thick fluid that is alkaline in order to protect sperm from the acidic environment of the female vagina. The gel is liquefied by enzymes from the prostate gland. It also contains sugars to nourish the sperm. The seminal plasma is left in the vagina.
Ovulation is a part of the menstrual cycle when the ovary releases a ripe egg, or ovum. Inside the ovary are hundreds of thousands of follicles. Each follicle is a hollow ball of cells with an immature egg in the center. The typical 28-day menstrual cycle begins on the first day of menstrual bleeding. During the first 7 days of the cycle, a few follicles begin to grow at the same time. These maturing follicles secrete estrogen hormone into the bloodstream to prepare the lining of the uterus for pregnancy. Around day 7, all of the follicles stop growing and begin to degenerate, except for one. This dominant follicle continues to grow and nourishes the developing egg inside it. Around day 12, the follicle secretes a large amount of estrogen into the bloodstream. When the estrogen reaches the hypothalamus and the pituitary gland in the brain, the anterior or front part of the pituitary gland releases a huge surge of luteinizing hormone into the bloodstream. Around day 14, luteinizing hormone causes the follicle to undergo a sudden growth spurt. Right before ovulation, the egg detaches from the inside of the follicle. The bulging follicle releases chemicals, causing one of the two fallopian tubes to move in closer and surround the follicle. The follicle swells until it bursts open. ejecting the egg and fluid from the follicle into the abdominal cavity. In response, the fimbriae, tiny projections at the end of the fallopian tube, sweep across the ovulation site and pick up the egg. Microscopic cilia on the fimbriae surface transport the egg to the entrance of the fallopian tube. Inside the walls of the fallopian tube, muscular contractions gently push the egg towards the uterus. After ovulation, the egg lives for 12 to 24 hours, so it must be fertilized by a sperm from the male during this time for a woman to become pregnant. If it's not fertilized, the egg dissolves away and is shed along with the uterine lining during menstruation.
Fertilization is the epic story of a single sperm facing incredible odds to unite with an egg and form a new human life. It is the story of all of us. During sexual intercourse, about 300 million sperm enter the vagina. Soon afterward, millions of them will either flow out of the vagina or die in its acidic environment. However, many survive because of the protective elements provided in the fluid surrounding them. Next, the sperm must pass through the cervix, an opening into the uterus. Usually, it remains tightly closed, but here the cervix is open for a few days while the woman ovulates. The sperm swim through the cervical mucus, which is thinned to a more watery consistency for easier passage. Once inside the cervix, the sperm continues swimming toward the uterus, though millions will die trying to make it through the mucus. Some sperm remain behind, caught in the folds of the cervix, but they may later continue the journey as a backup to the first group. Inside the uterus, muscular uterine contractions assist the sperm on their journey toward the egg. However, resident cells from the woman's immune system, mistaking the sperm for foreign invaders, destroy thousands more. Next, half the sperm head for the empty fallopian tube, while the other half swim toward the tube containing the unfertilized egg. Now, only a few thousand remain. Inside the fallopian tube, tiny cilia push the egg toward the uterus. To continue, the sperm must surge against this motion to reach the egg. Some sperm get trapped in the cilia and die. During this part of the journey, chemicals in the reproductive tract cause the membranes covering the heads of the sperm to change. As a result, the sperm become hyperactive, swimming harder and faster toward their destination. At long last, the sperm reach the egg. Only a few dozen of the original 300 million sperm remain. The egg is covered with a layer of cells called the corona radiata. The sperm must push through this layer to reach the outer layer of the egg, the zona pellucida. When sperm reach the zona pellucida, they attach to specialized sperm receptors on the surface, which triggers their acrosomes to release digestive enzymes, enabling the sperm to burrow into the layer. Inside the zona pellucida is a narrow, fluid-filled space just outside the egg cell membrane. The first sperm to make contact will fertilize the egg. After a perilous journey and against incredible odds, a single sperm attaches to the egg cell membrane. Within a few minutes, their outer membranes fuse and the egg pulls the sperm inside. This event causes changes in the egg membrane that prevent other sperm from attaching to it. Next, the egg releases chemicals that push other sperm away from the egg and create an impenetrable fertilization membrane. As the reaction spreads outward, the zona pellucida hardens, trapping any sperm unlucky enough to be caught inside. Outside the egg, sperm are no longer able to attach to the zona pellucida. Meanwhile, inside the egg, the tightly packed male genetic material spreads out. A new membrane forms around the genetic material, creating the male pronucleus. Inside, the genetic material reforms into 23 chromosomes. The female genetic material, awakened by the fusion of the sperm with the egg, finishes dividing, resulting in the female pronucleus, which also contains 23 chromosomes. As the male and female pronuclei form, spiderweb-like threads, called microtubules, pull them toward each other. The two sets of chromosomes join together, completing the process of fertilization. At this moment, a unique genetic code arises, instantly determining gender, hair color, eye color, and hundreds of other characteristics. This new single cell, the zygote, is the beginning of a new human being. And now the cilia in the fallopian tube gently sweep the zygote toward the uterus, where he or she will implant in the rich uterine lining, growing and maturing for the next 9 months until ready for birth.
Before in vitro fertilization, a woman will receive fertility medication that causes more than one egg to grow and mature in the ovaries. A man will provide a semen sample so that the healthiest sperm can be collected for fertilization. If the male partner is completely infertile, also known as sterile, or the woman doesn't have a male partner, a donor may be arranged to provide sperm for this process. In vitro fertilization consists of 3 main procedures: follicle aspiration, fertilization, and embryo transfer. During the first procedure, called follicle aspiration, eggs will be harvested from the ovaries. At the beginning of this procedure, an ultrasound probe will be inserted into the woman's vagina so that her doctor can view her ovaries. Inside the ovaries, the doctor will look for follicles. Each follicle is a fluid-filled sac that contains an egg. Then the doctor will insert a long, thin needle into and through the wall of her vagina and guide it to the ovary. A suction device connected to the needle will collect several eggs from inside their follicles. During the second part of in vitro fertilization, called fertilization, the collected eggs will be taken immediately to a laboratory where they will be fertilized. Fertilization may be performed by insemination, where several sperm are mixed with the healthiest eggs. Or the eggs may be fertilized with sperm injected directly into them during a process called intracytoplasmic sperm injection. The fertilized eggs, also called embryos, will be monitored for 3 to 5 days as they begin to grow. At this time, the lab may create a hole in the zona pellucida surrounding some of the embryos. This process, called assisted hatching, will help these embryos implant in the uterus. Some of the embryos will be used right away for embryo transfer, and the rest will be frozen and stored for future use if necessary. The third part of in vitro fertilization is called embryo transfer, which is done 3 to 5 days after fertilization. During embryo transfer, a tool called a speculum will be inserted into the woman's vagina so that the doctor can see her cervix. A syringe will be loaded with fluid containing 1 or more of the hatched embryos. Then the syringe will be attached to a long, thin tube called a catheter. The doctor will insert the catheter into the vagina, through the cervix, and into the uterus. Once inside the uterus, the doctor will inject the embryos. Then the catheter and speculum will be removed. The woman may continue to lie on her back for about 15 minutes.
The big news from the Hubble Space Telescope this week was that it had spotted the most distant star ever found at 12.9 billion light years away and nicknamed Earendel. Now, you'll have probably seen this in the news already, but now it's time to dive into all of the nitty-gritty astrophysics details, like how did they find this thing? How do they know how far away it is? And how do they even know that it's a star? And is there a chance that it could be something else entirely? So let's dive into this. This study has been led by Welch, Coe and collaborators who have been targeting big clusters of galaxies with the Hubble Space Telescope since about 2016 in the hope of finding things like this, known as arcs. These are galaxies in the background, behind the ones in the big galaxy cluster in the foreground that you can see. And the cluster is just one big lump of matter, right? You know, like hot hydrogen gas and dark matter, just all pockmarked then with galaxies of stars, kind of like a chocolate chip cookie. And all of this matter curves space, right? This is how Einstein described gravity in his theory of general relativity, which means that light from those background galaxies travels across that curved space and gets bent into these arcs. This is what's known as gravitational lensing, because that cluster of galaxies in the foreground acts like a lens to change the path of light, just like the bottom of a stemmed wine glass does when it passes in front of a candle in the background. And just like a lens, that cluster of galaxies can also magnify things in the distance as well, taking those, very faint distant galaxies that we wouldn't usually be able to spot and making them much brighter so that we can study them. They got that image back in 2019, 3.5 years after the image that the arc was originally spotted in. Now, along any arc, you also get clumps as well, which could either be light from the center of a galaxy where it's brightest, or from a star cluster in that galaxy that's really quite bright as well. And usually those are seen in multiple places along the arc due to how the lensing works, like the things highlighted in cyan here. This is a star cluster seen 3 times. But then there's also this bright point which is only seen once in both the images taken in 2016 and in 2019, which the authors of this study identified as a single star in this galaxy that's 12.9 billion light years away. We'll get to how they identified it as a single star in a minute, but I just wanted to talk about how it was even possible for them to detect a single star at that kind of distance. Because when you look up to the night sky, every single star that you see is from our own galaxy, the Milky Way, a few tens of thousands of light years away. The Hubble Space Telescope has just enough resolving power to make out individual stars in the Andromeda galaxy, which is our largest, nearest neighbor galaxy. But anything further than that, and the light from the stars have just merged to give us just this glow of a galaxy. It's only when they die and go supernova do we have a hope of picking out individual stars, but even that has its limits in terms of distance, out to about 10-ish billion light years away. That isn't what we've got here. This isn't a ridiculously bright supernova. What we've got is a star that's just in the right place at the right time. The star just happens to be perfectly aligned with the clump of matter that's doing the lensing, so much so that it gets magnified to over 1,000 times brighter than it normally is so that we can spot it. The best analogy that I've heard for this is that the matter in the cluster is acting kind of like the ripples on the surface of a swimming pool. It transforms the equal amounts of sunlight that's incident on the surface of the pool into these patterns on the bottom of the pool, which are analogous to the arcs. In these patterns, patterns, you can see there's always that odd bit that is that much brighter than the rest. This is what's happened to this star, WHL 0137-LS, but nicknamed by the authors as Earendel, from the Old English word meaning morning star or dawn star, and this is why it's been nicknamed this, dawn star, you know, the first star at the dawn of the universe, you get it, right?
But now the scientists have discovered something they really did not expect, something extremely unusual, and something that even right now I think most of them still cannot believe. An actual star. A star at these ridiculous distances. A star visible right there. But how and why? And why only now? Well, as you might have guessed, and as you might already know, all of this is because of the so-called gravitational lensing effect. The only natural way for us to see in these extreme distances, and the only way for us to find stars, or sometimes even distant galaxies, is when certain alignment makes it possible. In this case, we're of course referring to the effect you're about to see right here, which is the Einstein's lens or gravitational lens. And the way it of course forms is when you have a really massive object in front of some kind of a other object, usually a bright distant star or a galaxy. As a matter of fact, previous detections of these distant stars at distances of up to about 4 billion light years away from us have all been because of the magnification from a lens, and the factor here was usually around 50 to 100. That's actually what happened in this detection right here back in 2018. But sometimes, in some extremely rare cases, we might get extremely lucky. We might find a lens that's even more powerful, and so powerful as a matter of fact that you start seeing individual objects that would be otherwise invisible. And so in this case, that's exactly what happened to the scientists using the Hubble telescope. They got extremely lucky. They used a foreground galaxy cluster, extremely massive cluster, known as WHL 0137-08, a cluster that's about 7.8 billion light years away from us, the one that you actually see right here, to discover something extremely unusual in one of the parts of the ring that it formed. Or actually, it wasn't really unusual at first, it only became unusual later. They discovered an object that you see right there that seemed to be magnified by a factor of 1,000, suggesting of course that this was an extremely distant object.
This star was discovered by chance using the Hubble Space Telescope. Hubble first observed the star's parent galaxy that was gravitationally lensed by a cluster in the foreground. Massive astronomical objects, such as galaxy clusters, distort the space-time fabric around them. As a result of this distortion, the light from the foreground's celestial bodies bends when it passes close to these massive objects. The problem lies when we calculate the total luminosity of Earendel, which is between 600,000 to 1 million times the luminosity of the Sun.
In addition, the mass versus luminosity relationship provides a way to relate a star's temperature to its mass. Hubble's visible and ultraviolet light measurements indicate that Earendel is a hot blue star with a temperature between 13,000 and 16,000 degrees Kelvin. In addition, its delensed luminosity is around 630,000 times the luminosity of our Sun. Its mass is then 50 times the mass of our Sun. This fits the profile for a luminous blue variable star. Webb's analysis added the possibility that Earendel is a binary star system with one star at 20,000 degrees and the other around 13,000 degrees. A spectrographic study by the James Webb Space Telescope is scheduled for November 2022. It will provide detailed data on its mass, radius, and the elements it's made of. This will be enough to place Earendel on the Hertzsprung-Russell diagram, and we'll know if it is our first population 3 star. Here are the links to the sources for the material in this video.
So when the light from this galaxy has been traveling through the universe to us, the universe has been expanding. So the light is stretched to longer wavelengths. It is redshifted. But on its way, it also passes through random clouds and clumps of hydrogen gas that just permeate the universe. And the hydrogen gas actually steals away a very specific color or wavelength of light as it passes through. As the light travels further through the universe, more light gets redshifted to become that specific wavelength that hydrogen likes to absorb and steal away. And so what happens is you start to lose all the light beyond a certain wavelength. If you take a spectrum of the light from the galaxy where you split the light into all of its different component wavelengths and get a trace of how much of each wavelength you detect, then it's really easy to spot, right? Like in the example I'm showing here. But the giant arc they detected here was actually too faint for Hubble spectrograph to even be able to detect. So instead what you can do is you can take images through filters that only let in like certain regions, certain wavelengths or colors of light. And from where you do and don't detect light anymore, you can pinpoint, well, how much has the light been redshifted and therefore how long the light has been traveling for to know how far away the object was when the light left it.
Redshift is denoted by a dimensionless quantity z. Z equals 0 marks present time, and as its value increases, so does the look-back time and the distance to that object. New Webb observations confirm that Earendel lies at a redshift of 6.2. This number is consistent with the Hubble Space Telescope data released in early 2022, making Earendel the highest redshift star ever.
Welcome, and thank you for joining us from Johns Hopkins Applied Physics Laboratory, home to the DART Mission Operations Center. I'm your host, Tahira Allen with NASA Communications, and tonight we're following the real-time journey of the DART spacecraft and its planned collision with asteroid Dimorphos. The Double Asteroid Redirection Test, also known as DART, is the world's first planetary defense test mission of its kind. At 7:14 p.m. Eastern, it will demonstrate an asteroid deflection technique known as kinetic impact. Rest assured, this is only a test. The asteroid DART intends to impact is not a threat to Earth now, nor will it be after the collision. We have live views of the action from space, so keep an eye on the DART cam in the lower left-hand corner of your screen. Right now, you're only seeing a black screen with a single point of light. That point contains 2 asteroids in it, Didymos with a smaller asteroid named Dimorphos orbiting around it. As long as we continue to receive these live views from DART, we're going to keep that feed up on your screen. As we get closer to impact, the asteroid will begin to take shape, and eventually Dimorphos will fill your entire screen. You'll also notice a countdown clock indicating how close we are to impact and a progress bar that'll check off key milestones along the way. Now, as we follow pre-impact operations, we invite you to join us as we check in with Mission Control for live updates and track DART's final milestones. We'll see 2 astronauts demonstrate what kinetic impact looks like in space, and we'll go behind the scenes at one of the observatories following DART's impact from Earth. Now, before we get any closer to impact, let's get to know our spacecraft and its mission. After a beautiful launch from Vandenberg Space Force Base on November 24, 2021, DART has traveled over 400 million miles. And now, in just over an hour, we'll witness the spacecraft collide with asteroid Dimorphos in an attempt to change its orbit forever. The DART spacecraft is about the size of a vending machine and uses hydrazine thrusters for propulsion and roll-out solar arrays for power. It's traveling at about 14,000 miles per hour and will complete the last 4 miles of its journey in just 1 second. DART is on a collision course with asteroid Dimorphos, which is about the height of the Washington Monument and, more importantly, poses no threat to Earth. Dimorphos sits within a double asteroid system and is the smaller moonlet asteroid orbiting its larger companion Didymos. DART has just one instrument on board, and that's a Draco camera, which is feeding images to its autonomous navigation system, steering it straight into the asteroid. The spacecraft is almost 7 million miles away from us right now, and you're watching a live stream of its approach to Dimorphos. It takes about 45 seconds for the images you're seeing in the DART cam to make their way back to Earth. Any moment now, we should learn if DART is ready to commit to impact. While we wait, I'm here with Andy Rivkin, DART Science Investigation Lead, and Mallory D. Coster, DART Impact Modeler. Andy, Mallory, while we wait to learn if DART is ready to commit to Dimorphos, I can't help but wonder, why this asteroid?
That's a great question. The way that the double asteroid redirection test was designed, it was to measure the period change in a binary asteroid system. So we needed a binary asteroid, so that eliminates some number of objects. We needed something with a moon that was small enough that we could move it with a strike from a spacecraft, but not so small that we wrecked the moon. So when you kind of tick off all the possibilities, Didymos really ended up as the best choice and really the only choice that would provide a mission in this time period.
See, I want to go back to that. You mentioned having a moon that we could push but not destroy. Could you, now in pop culture a lot, we see that, you know, oftentimes the idea is to just totally try to demolish the asteroid. Why have we chosen to not test that technique this time?
Yeah, the conventional wisdom for planetary defense is that you don't want to disrupt an object and blow it into a zillion pieces, but you want to keep it intact and just move it all as one piece. Because if you move it all in one piece, then you can keep track of it a lot easier. If you blow it into a million pieces, then some of them might still Earth, and you don't want to miss a thing.
Yeah, we might have more issues then. So we know that we have the perfect test subject. Mallory, now can you help us understand how, if mission success, DART's mission tonight can help improve models for mitigating hazardous asteroids in the future?
That's exactly right. So we stand to learn a lot from this DART impact. DART is both a technology demonstration as well as a really big science experiment. So from a technology standpoint, we're going to see if we have what it takes to autonomously navigate a spacecraft into a relatively small celestial body, something the size of a football stadium, that's pretty far away from Earth. From a science perspective, we get to perform one of the largest and fastest impact experiments that man has done. Something that could never be accomplished in a laboratory here on Earth. So we're going to learn how these large sizes, these fast impact velocities, and also these sort of extraterrestrial asteroid materials respond to deflection.
Wow, I mean, there's so much about tonight that we don't know, and it seems like your fun is just getting started, right, until after impact. So Mallory, Andy, thank you so much. And Tonight, ground-based telescopes aren't the only one watching the action. A small cube satellite built by the Italian Space Agency was deployed by DART 15 days ago and has been in the area to give us a bird's-eye view of impact. Here's more on Licia Cube.
Licia is a 6U CubeSat of the Italian Space Agency participating in the DART mission, and it's also the first Italian satellite operating in deep space. Licia Cube mission objectives is to support DART in the documentation of the impact effects, in particular in terms of the ejecta of materials that will be released from the asteroid surface after the impact, and also imaging the non-visible side of the asteroid during its flyby.
Licia Cube will acquire images using its two different cameras, Leia, a panchromatic camera, and Luke, an RGB camera. Therefore, we can better understand the nature of the asteroid Dimorphos impacted by DART. By means of our Scientific Operations Center in SSTC ASI, we will distribute and process the images in order to make them available to the entire team.
We are here in Argotech's Mission Control Center in Turin, from where, together with ASI, we monitor the status of Licia Cube. The batteries are charged, the radio is communicating correctly, and the navigation altitude is on the right trajectory. Everything is ready for the most important part of the DART mission, the impact with the asteroid.
And so it's important to note that tonight we're attempting something that's never been done. And with that presents many challenges to overcome. Here's what makes DART a first-of-its-kind mission.
The DART mission is a very difficult mission because we are trying to do something that hasn't been done before.
This is the first time we're going to an asteroid that is this small, this dark, and we're actually going to attempt an impact.
The DART mission is really something that the whole world can get behind.
We're doing this mission to prove that we can deflect an asteroid if we find one that is on an impact course for Earth.
We are trying to hit an asteroid 163 meters wide, which is about the size of the Washington Monument, while flying at 6 kilometers per second, which is like going from New York to DC in about a minute.
There is no chance that this asteroid could ever hit Earth.
It's a very small asteroid. It's only about the size of a small football stadium, and it's almost 7 million miles away from the Earth. That's 28 times the distance between the Earth and the Moon.
There's kind of a limit on how much mass you can launch into space. You know, rockets are only so big. So our spacecraft is only the size of a golf cart.
Draco is the primary instrument on the DART spacecraft. It is the camera that is going to be imaging the Didymos system as we approach.
When we first see the asteroid through Draco, it's just going to look like a pixel.
There's a star tracker on board that takes images of the stars and compares them to a known catalog to determine which way it's pointing in space. It poses the biggest risk because very, very small errors in this measurement can spell the difference between success and failure. And those measurements are going to be fed into the SmartNav algorithm that's going to be making the autonomous course correction commands that will put us on an intercept course.
There is a very small probability that we don't hit the asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, we are looking, we're finding the asteroid, even then, we might still miss.
We're trying to teach a computer how to recognize an object we've never seen before.
And the way it does that is by taking pictures of the asteroid and then interpreting where it is in space and guiding itself to it.
The spacecraft is controlling itself. SmartNav is guiding the spacecraft. And we have very limited ability to respond in that time. So it has to do it all by itself.
And at about 2.5 minutes out, we cease all maneuvering and we coast until we hit the asteroid.
It is going very, very fast towards the asteroid, traveling at 6 kilometers per second.
200 times faster than a car on the freeway. So when we hit, all of that mass, all of that momentum pushes the asteroid.
Even giving it a small nudge will allow it to change its course.
But if we did see an asteroid on track for Earth, this would be enough of a deflection.
It's like a bittersweet moment. Yeah, all this hard work just got destroyed, but that was exactly why we put it all together.
Of all the endeavors that we do for space and in space, this is probably one of the ones that one day will be the most important thing that we've ever done.
In the future, I hope that DART can teach us what ways work and what ways don't work for planetary defense.
Because it is humankind's first demonstration that we have gained the knowledge and the technology to be able to protect the Earth from an asteroid impact.
All right, we've reached 5 minutes from impact. The final command opportunity to SmartNav has passed, and the team is simply watching that data stream in just like we are. Also remember, there is a 38-second lag for the data to travel to Earth, and also an additional few more seconds for image processing. It's important to note that. You should be hearing the chatter in the Mission Operations Center momentarily.
This is DART MSC and DT Mach. 5 minutes till impact. 5 minutes till impact. We are at 1,100 miles away. Also, our window for sending any commands to the spacecraft is done. Contingency's done.
This is a great vibe in that Mission Operations Center right now, Lori.
It really is. They are so excited. And I'm honing in looking at these images as we get closer and closer, and you look at Didymos and just you're starting to see this physical body appear there. It's incredible. Just incredible.
That sounds great.
I'm still having a hard time believing this is real energy coming in near real time.
Yeah, but you've been watching it over the last 30, 45 minutes go from just being a collection of individual pixels, and now you can actually see the shape and the shading and texture of Didymos, and we're going to see that same thing with Dimorphos as we get closer and closer. This is so cool.
Never before seen images of Dimorphos will come into stark relief.
Absolutely.
A few seconds before impact.
Didymos. It's amazing. All right.
The team is standing just recognizing this moment, years in the making. It is really nice to see them relax a little bit, get off from those computers that they've been glued to, and just appreciate this moment that's coming.
Yeah, and they've earned this. It's just great to see them there. This is so cool.
Lori, we hit another major milestone. We are now 2.5 minutes from impact, and SmartNav has stopped maneuvering the spacecraft. DART is now coasting toward Dimorphos, and we hope into the history books.
Absolutely. This will be, I'm sure you've heard it many times tonight, humanity's first ever attempt at trying to move another celestial body, and also our first attempt ever to execute a mission in sole purpose of planetary defense. So what an exciting time. Yeah, and I'm starting to see Dimorphos start to come into view there. You can see it starting to take shape. I'm starting to see individual boulders on Didymos. Unbelievable clarity of images there.
Coasting on in, our projected miss distance is going to be about 17 meters.
All right.
All eyes on this event. Space telescopes, ground telescopes from every continent on Earth.
Yeah.
All right. 2 minutes out. Does not look like one single rock to me.
Oh, boy, we're getting close.
14,000 miles per hour, Lori.
14,000 miles per hour, and remember, 45 minutes ago, 55 minutes ago, we couldn't even resolve this object in space, and now you can see us zeroing in right on target.
And we're now dropping the clock, and we'll go by loss of signal to confirm impact.
Right. Yes. Imagine we'll get that loss of signal, and then we'll hear from Lena Adams again, letting us know that we've been successful.
I feel like that'll be a crystal clear signal.
I think so. I think we're starting to see more resolution. In fact, look at that. Didymos has even gone out of the view. We're now just seeing Dimorphos.
This is remarkable stuff.
Oh my goodness, look at that.
Looks like control system settling down. Angular rates look really good. I think we're going to get the investigation team some good pictures.
Wow.
No, come on, we can do better than that.
Starting to see those individual boulders there. You can see shadows of the various rocks on the surface.
Impact. It's amazing, guys. Oh my goodness, look at that. Unbelievable.
Yeah. Looks to me like we're headed straight in. Oh my gosh. Oh wow.
Yeah. Oh my goodness. 8,
Yeah.
7, 6,
wow.
5, 4, 3, 2, 1.
Oh my gosh. Oh wow.
Awaiting visual confirmation.
All right. Let's see. We got it? Waiting.
And we have impact. A triumph for humanity in the name of planetary defense.
Woo. Fantastic. Oh, fantastic. Oh.
What a moment. Very few words can really capture this moment. This is beautiful to watch.
snow, and the jets are like this freight train plowing across it.
But here, a freight train traveling at close to the speed of light, smashing into clouds of gas.
Enormously bright vortex of gas swirling this dark void.
This bright vortex spins around the supermassive black hole at over 2 million miles an hour.
So there's a tremendous amount of friction as material moving slower and faster rubs against each other. That's what's heating the disk up, and that's what's causing it to glow.
Scientists think that the intense energy of the accretion disk is the source of the jets. The hot swirling gas and dust produces powerful magnetic fields.